morning to one and all. On behalf of EZ Department of Francis Xavier Engineering College and our entire team, I would like to invite all of you to this webinar session on error correcting codes for 5G. I invite Mr. Premanand Sir, Assistant Professor of EZ Department, to start the session with prayer.
Prayer. Father, we thank you and praise you, God, for all the blessings, for all the goodness, for all the happiness you showered upon us. Father, we pray for our college, our chairman, all the teaching and non-teaching fraternity, God. Bless them, be with them, and give them good health, God. Father, we pray for this webinar, God, error correcting codes for 5G. Bless our resource person, Dr. Surender, NIT, Pondicherry. Bless our HOD ma'am, Friska ma'am, and bless our coordinator, Kanansa, Reggie ma'am, and Vishnu Priya ma'am, and bless all our participants, God. Let this seminar be an useful and fruitful one for all the participants. We ask and pray in the name of our Lord and Savior Jesus Christ. Amen.
Thank you, sir. Now I invite Mrs. J. Friska ma'am, Head of the Department, Electronics and Communication Engineering, to deliver the welcome address.
Thank you, ma'am. Trust in the Lord and do good. Education is the most powerful weapon we can use to change the world. Hello, everyone, and welcome to our department's 9th Professor webinar series on error correcting codes for 5G by Dr. M. Surendra, Assistant Professor, NIT Puducherry, Karaikal. We, Francis Xavier Engineering College, the teaching fraternity of Department of ECE, feel extremely delighted in welcoming our resource person, Dr. M. Surendra sir, learned professors, future leaders of our nation, students, industry experts who have signed with us for today's interesting session. On behalf of our management, the entire teaching fraternity of Francis Xavier Engineering College Department of ECE, I would like to extend a very warm welcome to all the delegates who have joined with us today. First of all, I would like to place my heartfelt gratitude to Lord Almighty for His immeasurable blessings and unconditional love on all of our lives. Next, I would like to record my sincere thanks to the management of Francis Xavier Engineering College for their encouragement and support over the years, and their support has brightened our professional career, and their generosity will forever remain in our hearts. It gives me immense pleasure to welcome our General Manager Development, Dr. Jaykumar sir, a dynamic person, for his constant support and directions for successfully organizing all our events. We welcome you, sir. I feel honored in welcoming our respected principal, Dr. V. Velmurugan sir, a man of actions, to this greatest gathering. We welcome you, sir. I feel extremely delighted in welcoming speaker of today's session, Dr. M. Surendra, Assistant Professor, NIT Puducherry, Karaikal, who has accepted our invitation and joined with us for sharing his knowledge, experience, and expertise with us. We welcome you, sir. It gives me immense pleasure in welcoming Dr. L.R. Priya Madam, Professor Academics, for her constant source of inspiration to all of us. We welcome you, Madam. I would like to welcome the coordinators of today's event, Mrs. Regitimna Madam, Mr. Kannan sir, Mrs. Vishnu Priya Madam, Assistant Professors, Department of ECE, for their strenuous effort in connecting an eminent resource person with us. I would like to welcome all the participants from academic institutions, industries, students who have joined with us across the state and across the globe to get practical insights. We feel happy to share that we have received 1,700 plus responses for our today's 9th Professor webinar series. We wish all the delegates to sail away from their safe harbor, catch the trade winds for their sails, explore, dream, discover. Thank you.
Thank you, ma'am.
Now I invite Jayaraman sir to introduce our dynamic resource person.
Thank you, ma'am. Good morning, delegates. It is my privilege to introduce our resource person, Dr. M. Surendra, to this live webinar, who is going to talk about error correcting course for 5th generation communication. Currently, he's been working as an assistant professor, NIT Pondicherry. When we talk about his educational background, he obtained his PhD in NIT Trichy, and his master's and bachelor's of engineering were from Tyagaraja College of Engineering in Electronics and Communication domain. His field of expertise and his current research focusing on 5G and beyond. Also, his research interest includes VLSI, cryptography, OFDM, MIMO,
Yeah. Hello all. Thank you. That was so formal, and I'm so pleased to hear this. Anyway, I would like to say, this is an opportunity for students and everyone to interact with the other faculties and what's happening in the other colleges. So, participants, please make sure if there is no participants, other participants can make sure that they can make use of it. If not me, at least for higher grade professors, they will have a lot of things to say, and there are a lot of things to take away from them. So even I am looking for some webinars to attend. Fine. Our college is also planning soon. We will be having that too. Yeah. So can I straight away go into the presentation? Can I cut the video?
Yes, sir.
Can I cut the video?
Yes, sir.
Okay. Thank you. Okay, we'll start on error correcting codes for 5G. That's my topic for presentation today. I hope everyone can hear me. If not, please let me know. So I just completed my research on 2017. So this is just a disclaimer. Once after completing this PhD, I thought my work is relatively new. But soon after 6 months or 1 year, when I look back, it becomes so old because those are all like 4G or 4.5G, not up to the 5G. So the growth of the communication field is very much exponential. So we have to keep on adapting to that, and I'm trying my level best to reach there still. So even now, today we are talking about 5G, and there are researchers that are going beyond 5G. So we have to be as competitive as that particular wireless field. That's my advice to research scholars or final year project students or anyone. And but anyway, it is very interesting. Anyway, the base are same. The basic is the digital communication, probability theory, and linear algebra and everything. So with that, I just start this. So there are some few targets of 5G we'll discuss. We have already 4G with us, 4G LTE. Mainly Geo is the main player here. And there are few targets of 5G. They have decided, FCC have decided, Federal Communication Commission have decided on the targets of 5G. The first one is the data rate is 10 Gbps uplink actually, and 20 Gbps downlink. So data rate 10 Gbps and 20 Gbps means not for per user. They are not planning for 10 Gbps. Please remember that. And with the base station, we could able to achieve a data rate of 20 Gbps downlink and 10 Gbps uplink. And if we have a dedicated base station to us, then we can achieve a data rate of 20 Gbps. Nextly, and also for a per user, the data rate they are planning is 100 Mbps downlink and 50 Mbps uplink. So this is a massive speed actually. And with this kind of speed, what they are going to achieve is the things we are going to discuss further. And spectral efficiency is how efficiently we are going to use the bandwidth. This is slightly higher than the 4G, and this has around 30 bits per hertz, and 30 bits per hertz for uplink, downlink, and 15 bits per hertz for uplink. Okay, this is the spectral efficiency they are aiming, and the device connectivity is planned to have around more than 1 million users. They are planning to connect more than 1 million users per square kilometer. That means we have 1 million different devices within a square kilometer that is being connected to the 5G. So that's what we called as a that's what the layout of this IoT, Internet of Things. Because just consider a person, he is using a Bluetooth headset, a wristwatch that actually monitors your heart rate and everything, the amount of steps you are carrying through, and there are a lot of other accessories that are being attached within the body, within a human, so that those devices will be come into the picture, and that actually constitutes to the device connectivity. So minimum they are planning to have 1 million users per square kilometer. Okay, and this is a very crucial part of this 5G, what I feel, because this is where we got the project on on ultra reliable low latency communication, URLLC. That is a very famous word, and it has a round trip time of less than 1 millisecond. Generally in 4G and 5G, we have a round trip time of around 20 milliseconds, 20 to 30 milliseconds if I'm not wrong, and we can experience this by while speaking from one place to another place. Just consider that I'm speaking from Karaikal to Thoothukudi or Tirunelveli. It will reach you there by around after a 2 seconds delay. I'm sure it must be minimum of 2 seconds delay. So apart from that, if I consider an ideal scenario, there I will be having a delay of 30 milliseconds to my voice to reach there. So this can be eliminated by going to the higher frequencies, and this has led to a lot of different areas like driverless car. Just imagine that we want to drop our relative in bus stop or something. So we want to drive him. Instead of I want to drive him, I just sit in the home and I can drive my car using my mobile app, and he himself is getting dropped in the bus stop. So that's the kind of thing this latency can prove. Why this latency plays a crucial role is, so when the car is nearing another vehicle, so that there is a chance of accident. So when it is going at a high speed and when it is nearing a vehicle, there is a chance of accident. If the latency is 20 milliseconds or 30 milliseconds, just imagine, before I react, it will just hit the next vehicle. So latency plays a very crucial role there, and also this latency will be a key player for telemedicine very soon. And just imagine a commercial application like when we are in offshore, like when we are in US or something, and we miss our mom's food. So there is a chances there that your mom can virtually cook from here. That is because of your virtual reality and augmented reality. So latency plays a crucial role there, and this latency actually concentrates on error control coding. So that's why I'm just talking a little bit in detail about this latency, and the energy consumption should be very less. That does mean that my IoT devices, if you see the sensors and all those things, it is actually battery operated, and once we just plug in that sensor, it should be there for at least 10 years. So we don't have to change the battery frequently, and we don't have to do all such things for 10 years. That means it should consume very less battery, so it should have a better rate performance there. And yes, MMTC is another scenario of 5G, usage scenario of 5G. MMTC means massive machine type communication, and we have a mobility of it has to support a mobility of 0 to 310 miles per hour. Oh, that means 4G is also easily supporting this miles per hour. But given that your millimeter wave, I'm sure you must have heard about the millimeter wave in the 5G. There, the number of small cells are very high. So it cannot. It means that we can suddenly move from cell to cell. So it is little hard to control the mobility there. So they are considering it as one of the target and merit of 5G. Okay, mobility it should support around 0 to 3. Automatically changing that. And moving on to the next one, the channel coding schemes for 5G. There are two main. Actually, the 5G standards, the 5G has standardized the channel codings that is going to be used for the release 15. That particularly aims on URLLC. That means ultra reliable and low latency communication. And two codes are being finalized and standardized. One is LDPC, low density parity check codes, and another one is polar codes. So low density parity check codes was defined by Gallagher, a scientist named Gallagher, and it was introduced way back in 1960s. If you just go through that in MIT Press, he would have released that. Way back in 1960s, the LDPC has been introduced and it's been adapted now actually. So there is nothing like coding technique that has been introduced way back will find its own way of connecting to the 5G. And the polar codes is relatively new. It is introduced by a researcher named Arikan. It was introduced on 2009. During 2009, it is introduced. And LDPC is for communicating the data, user data, and the polar codes is for transmitting the control information. So with the control information, we could find what are all the frozen bits that has been there, because with that frozen bits we could identify where the sequence is starting, where the data sequence is starting, and some control information, some kind of preamble can be sent through the polar codes. Polar codes is a short block length code, and it addresses the latency of successive cancellation decode. And LDPC is a high throughput, variable code rate. See, in 4G we will be using the turbo coding and bit-to-bit decoder in 4G, and suddenly there is a change because turbo coding is a very powerful coding. For 5G, they want little more flexibility with the coding, so they are going for the LDPC, and it supports high throughput, variable code rate and variable code length, and also it supports hybrid automatic repeat request. So these are all the things supported by the LDPC. That doesn't mean turbo coding doesn't support that, but LDPC has some additional features that will help the 5G to go ahead with the channel coding. Okay, I'm sure you must be aware of the channel coding and the source coding. Fine, and basically this presentation I plan to have some basics, very basic, like digital communication and why we go for a digital communication. Once we enter into the digital communication, we will be sticking there as a digital communication. We don't come into the analog domain, because communication involves both the digital domain and an analog domain. Initially the bits are converted using the BPSK or QAM modulation, and then we will be transmitting only in the continuous domain. We will be transmitting only as a continuous domain. But the thing is, whether we need to when we are dealing things in digital communication, we have to deal it as a digital communication only. We don't want to worry about the continuous time signal at all, and that means the analog communication at all. Also, for that question, the justification is the following one, and also it helps that justification actually helps in why we are going for coding. So when I'm talking about coding, we need to worry about two key metrics. one is bit error rate, another one is signal to noise ratio. And those are all the two key metrics that will be discussed for a continuous time and the discrete time in the following. Right. So this is a continuous time. Just take an AWGN channel. It just adds the noise, kind of a wired communication. And when we transmit, I will take a marker. Yeah. A is the bits to be transmitted, and it is modulated. Any modulator can be used, and it will be converted to a continuous time signal S of t. That's why we have the S of t there. It is the function of t. The S is the function of t. That is a waveform that is to be transmitted, and it is get added with the noise because this is a AWGN channel, additive white Gaussian noise channel. If you check that this N of t is IID. We used to whenever I open a communication paper, they used to assume that IID, identical and independent, identically and independently distributed channel. That means for every time the noise is independent, because if a noise is taken at time t1 and if a noise is taken at a time t2, both are completely independent. They are not dependent at all. So this N of t is completely independent, and the R of t is nothing but S of t plus N of t. That is the received signal that enters the receiver. And once the continuous time signal R of t enters the receiver, there will be a filter generally, and this is this block diagram misses a lot of part. Just ignore that. This has some basic required part for this discussion. So don't just think where is the downsampler, where is the upsampler, all those things are missing only. Okay, but just what is required for this discussion, I just included that. And here, if you see continuous time signal, R of t is being received, and it is filtered and it is sampled. Now we have the information R now, that is a discrete set of samples. This R is related with the transmitted A, because ultimately we want to know what is A, right? A is nothing but the bits that are being transmitted. So when we sample the R of t, when we filter and sample the R of t, we will be getting the samples R, and using a decision device. A decision device will take a decision on what bit is being transmitted. Either 0 or 1 has been transmitted. That decision is made by the decision device, and this R being given to the decision device, and we will be estimating the transmitted bit, and it is given as A cap. Okay, this is the continuous time scenario. Let's look into the discrete time scenario. There we will be having a BPSK modulator. Just when we go inside a general communication system, we will see both the continuous time and the discrete time system. So this is a discrete time system. Just consider that, and the same A bits are being transmitted, and BPSK modulator is used to do the modulation. There we will be 0 will be converted to +1, and 1 will be converted to -1, and that symbols actually represents S of t, equivalently represents S of t, and here N, everything doesn't have that function of t, because this is a discrete time AWGN channel, and this noise is also discrete. And there is quite a few theory on how this N of t is getting sampled and getting converted to N. So after the noise is getting added in the channel, we will be having R is equal to S plus N. That is the received signal. That is a received symbol R. And straight away we will be going for the decision device, because we don't require a sampling or everything, because already we are receiving as a samples only. So we don't require a separate filter and sampler here. So directly we are giving to a decision device, and it will be estimating what is the R that has been sent, and followed by a demapper. Demapper in the sense we have converted 0 to 1 plus 1 and 1 to -1. So that will be correspondingly matched by the demapper. So ultimately digital information, binary information, zeros and ones are transmitted, and finally after demapper we will be getting the zeros and ones that has been transmitted. So this is the basic idea of a digital communication system. So I hope everything is a little bit familiar to you, but there is always another dimension. So let's discuss in a little bit in detail on this. Okay. So when we enter into a modulator, we will be B bits and we will be getting some S symbols. This modulator is based on either BPSK, 4QAM or QPSK or 16QAM, anything. So these are all the possible constellations and the possible modulations, digital modulations that are all available. And here you can see that. Can take a pen. This is -1 and 0 is +1. 0 is mapped to +1 and 1 is mapped to -1. So in that way, these things are converted. Our aim is only this BPSK only. Only this BPSK only. So I'm just forcing a little bit on that. And we have a 4QAM. We can also use a 4QAM or a 16QAM. There are also scenarios like 1024 QAM is also being used. That is in the TV standards and all, they will be using that 1024 QAM because they have a very good channel, so they can go for a higher order constellations there. And just think about the in the place of 1 bit, when I'm using a BPSK, we are just sending 10 bits. So that's the beauty about higher order constellations, but still we have to sacrifice a lot of performance there. So based on the channel conditions, we will be deciding what kind of constellation we can go for. So right now here, the modulator we are going to use is BPSK modulator, and we will take an example here. Hot decision receiver. A hot decision receiver. There are a receiver can be also classified as a hot decision receiver and a soft decision receiver. Actually, hot decision receiver, what it will does is, it is a very straightforward one. You just fix a threshold. So whichever values that comes in the left side of the threshold, you will be in the case of BPSK. Just consider in the case of BPSK, whichever value, here is the threshold. In 0, we set the threshold. So whichever values comes here will be in the left side. Whichever values comes in the left side, we will be considering that as -1, and whichever values lies in the right side, we will be taking that as, we will be decoding, we will be mapping that as +1. We will be, I mean, it will be quantized, kind of quantization, 2-level quantization, let's say. And here we can see 1 0 0 1 1 0 1 0 1. So this is the bits that has been transmitted, and correspondingly, first it will be mapped on to the symbols. 1 is mapped to -1 and 0 is mapped to +1. Okay, here you can clearly see that, and this is what this is the symbols we are going to transmit, and here we can see that -1 will not be received as -1 because due to some noise, since R is equal to S plus N, the noise is getting added there. -1 is not received as -1, but it is in this case it is received as -0.8. That means the noise component is +0.2 there, and +1 is being received as a 0.2. That means the noise is -0.8 there. +1 is received as 0.2. That means the noise is -0.8 there. Consider this scenario, that shaded scenario, that is this yellow coloredly shaded scenario. There we have a -1, and it is decoded, and it is received as 0.2. So when I plot 0.2 here, I approximately point it here. This is that 0.2. That means this is 0.2, and that means either my noise is plus -0.8, or in the receiver, I'm just talking about the receiver, either my noise is 0.8, correct, and sorry, -0.8 from when I take it from the +1 point of view, and when I take it from the -1 point of view, my noise can be +1.2 because the receiver doesn't know. So these are all the two possible noises that are all possible, that could be possibly happen. So what we do is we do the maximum likelihood because we this threshold, this hot decision receiver, what it will say is like only the minimum noise has been in the channel. It assumes that only a minimal noise could be affecting the channel, and so it will be taking the minimal noise that has been used, and -1 is now mistakenly decoded as or detected as +1 here. Okay, so this is something that has to be dealt with the channel, because we can't help there. And what are all the ways? There is another scenario here, and -1 has been sent and +0.1 has been received. So there we have two possible scenarios, like either a noise of +1.5 +1.1 has happened, or -0.9 has happened. So among them, 0.9 has a very minimal noise, so it will definitely wrongly decoding as +1 there. So these are all the characteristic of a channel, and we have to live with it actually. So what we are going to do for this? So ultimately we want to get the error-free communication. We aim for that error-free communication only. So there are two different metrics that has been considered in the digital communication to characterize a channel. Characterizing a channel is the key thing in digital communication, because based on the channel only we can make some decisions. So one metric is a signal to noise ratio, and another one is bit error rate. First we will see what is a SNR. SNR, as we all know, that it is the signal power to the noise power. So when I have SNR is generally exhibited in terms of dB. So 10 times take the log, we will be getting in a dB, and we will be getting in a dB scale. So when the SNR is equal to 0 dB, that means my signal power and noise power are same. When my SNR is positive, when my SNR is 1 dB or 3 dB, that means my signal power is more than the noise power. So that is a beautiful metric about for characterizing a channel. And bit error rate is another important metric. And as we know, bit error rate can be either be characterized using a probabilistic way of characterizing this bit error rate. What is the probability that the bits that has been sent is not equal to the estimated bits in the receiver? And in simulations, we go for the Monte Carlo simulations, and we get the bit error rate as number of error in the bits, number of bit errors to that of the, it's the ratio of the number of bit errors to that of the total number of bits that has been computed. These are all some basic metrics, but still it has its own significance, because whenever we open a paper, we either see a SNR or a EB by N0 or ES by N0, and BER, BLER or ACR, symbol error rate. And there are other performance metrics to outage probability and capacity, channel capacity, and all those things. LDPC and polar codes actually has a more channel capacity approaching things. And we go for a continuous time SNR. When we consider the SNR for the continuous time system, see this gives why we ignore the continuous time after a particular amount. Once we enter into the digital communication, why we just ignore the continuous time signal? Because once we enter the digital communication, it is purely digital communication only. So for a continuous time system, for a continuous time AWGN channel, the SNR is given by signal power is P. This signal power is since it is a continuous time signal, we just integrate it and square it. We just square it and integrate it. We will be getting the signal power directly. And noise power spectral density, which is given by N0 by 2, since it is a double-sided power spectral density. And also there are a lot of oscilloscopes that are all available in the market. So we can directly take the noise power spectral density from there. So there is a noise power spectral density, that is the noise power per hertz in a unit bandwidth. So what is the noise power throughout the bandwidth? So we consider the bandwidth here is 2W, and the noise power here is noise PSD into 2W. That means the bandwidth. What is the noise power throughout that bandwidth? That we will be having as N0 into W. Okay. So we will be having the SNR as signal power to that of the noise power, and signal power is P and the noise power is N0 into W. So we have SNR as P divided by N0 into W. So this is the SNR of the continuous time SNR, and also the symbol time, the number of symbols that has been sent through this bandwidth is 2W symbol rate is 2W because the bandwidth is 2W. The symbol rate is 2W. That means 2W symbols are sent per second, and each symbol has a time duration of 1 by 2W. Okay? So this is about the continuous time SNR, and we will enter into the discrete time SNR. In the discrete time SNR, we express in terms of energy because we will be receiving some set of samples, and we will be computing the energy that has been assigned per symbol. Okay, in this way we will be considering the energy per symbol in the discrete time SNR. So energy is nothing but power into time. So we have P into T there. So T is nothing but 1 by 2W. We take the same system as the previous one because overall that is the system. The bandwidth is 2W. So T is equal to 1 by 2W. So the energy per symbol is P by 2W. And the noise energy is nothing but the variance of the noise. We take the additive white Gaussian noise, and how much variance does that have? Does your channel have? That actually gives the noise energy, and that is similar to the noise power spectral density of the continuous domain, that is N0 by 2. And the SNR is the signal energy, simple energy to that of the noise energy. So we have ES divided by sigma square, and we have P divided by N0 into W. When we check the SNR of the discrete time and the continuous time, the SNRs are same. So that is the beauty about this communication system, because here the SNR is P by N0 into W. In the discrete time also, the SNR is P by N0 into W. So this SNRs are same. So that literally means that when we enter into the digital communication, we just worry about the digital communication and let the continuous time system away. Okay, so we don't have to worry completely about that continuous time system. Digital communication can be dealt as digital communication. Okay, so we don't have to switch back to continuous time. What happens with the continuous time like that? So this is what happens with the MATLAB coding, and we'll be comparing the bit error rate and SNR for BPSK modulation. Here for a BPSK modulation, we have either -1 or +1. So energy per symbol is given by, consider that -1 and +1 are equally probable, so that the energy per symbol is given by squaring that symbol, and how many number of symbols that we divided by 2. Well, since there are only 2 symbols, so we divided by 2. Ultimately, we have a symbol energy as 1, and noise power is, obviously it is a Gaussian distributed, so we have a sigma square there. So SNR is 1 by sigma square. This is the SNR for the BPSK modulation. And what about the bit error rate? Bit error rate is given by when that communication system is possibly decoding it wrongly. That is the bit error rate. That is a bit error rate scenario. When we have an axis, we have 0 as a threshold, and we have -1, and we have +1. This is the actual constellation of your BPSK. And when I have sent a +1, and when my noise is very much less than -1, consider my noise is -1.5. Consider my noise is -1.5, and my +1 now will be received as 1 minus 1.5. So that means my received sample will be located here. This is -0.5. Okay, so this is the scenario of an error. When I transmit a positive value and my noise is very much negative, then I will get an error there. So similarly, when we are transmitting a symbol -1, s is equal to -1, and my noise is more positive, like if I am transmitting -1, and if my noise is 1.8, consider my noise is 1.8, then it will directly go to 0.8 here. -1, I have transmitted -1, but it is coming as 0.8 here. That means it creates an error. So the region where the noise is very much less than -1, I mean less than -1, and the noise is higher than +1, will definitely lead to an error for us. So these are all the two possible scenarios of the bit error rate. In a probabilistic way, we can see that, and as we know, -1 and +1 are equally probable. We have the probability of S is equal to +1 and S is equal to -1 as 1/2, equiprobable. And the noise PDF, we just found these two terms. We know what are all these two terms: probability of S is equal to +1 and probability of S is equal to -1. So now we want to find what is the probability of N is equal to N is less than -1 and N is less than greater than +1. So these things we have to find now, and for that I'm considering the PDF, that is the Gaussian PDF, Gaussian distributed noise. Here we have a Gaussian distributed noise. This is the bell curve, inverted bell, and we have +1 and -1 here. So one thing is less than -1, another one is greater than +1. So these are all the two places this error can happen, right? And this PDF is generally given by this complete PDF is generally given by 1/√2 pi sigma e power minus x divided by 2 sigma square. This is a very famous Gaussian equation with the zero mean, and this bit error rate here is characterized as, this probability here is characterized as 1 divided by q of 1 divided by sigma, where q is a q function. This is a very famous function. It is based on the error function, complementary error function, or you can see that there is always a tool, Mathematica or a MATLAB, that will have this q function with that, and each probability, this area completely, we can say that as q of 1/sigma. Okay, so SNR is 1/sigma square, so we are having BER as q of root of SNR. Okay, so this is about the bit error rate, because when I substitute q of 1/sigma for both probability of n less than -1 and probability of n greater than +1, then we will be having 1/2 into q of, because probability of S is equal to -1 is 1/2 and S is equal to +1 is also -1/2 only. So we will be having 1/2 into q of 1/sigma plus 1/2 into q of 1/sigma, that is ultimately q of 1/sigma. So 1/sigma, how it is related with the SNR is, it is equal to the square root of SNR. 1/sigma is actually equal to the square root of SNR that we just derived in the previous slide. Okay, so in this way we establish a relationship between the bit error rate and the SNR. There is always a trade-off between this bit error rate and the SNR, and when we move, we can actually plot this. We can actually plot the curve having the bit error rate in the y-axis, and when we control the SNR in the x-axis, we can plot that bit error rate and SNR curve. Now we enter into the coded systems. Coded system is the one which has the encoder, and this is the very crucial part here. This one is the additional part that we are adding. What generally a channel coder does is it adds redundancy. That means if I am giving a k-bit message, and I'll be in my encoder output, I'll be getting k plus some 3 bits or 5 bits or anything. Any number of bits can be added to that. K plus some number of bits will be added. That is actually known as the parity bits, famously known as the parity bits. And there are a lot of encoders that are all available. Golay codes, Hadamard, Hamming codes, Viterbi, Trellis codes are there, convolution codes are there, turbo codes are there, and in this scenario, in this case, we have the low density parity check codes. So everything are there available. And why we need to introduce this redundancy? Because in the place of sending some 5 bits, I want to send 8 bits. So that means I'm wasting a lot of resources there, right? For sending 5 bits, I'm sending 8 bits. So that is a wastage of resource, particularly a wastage of bandwidth. Why we have to do such a sacrifice in a bandwidth scarce environment? So that is a question that has to be answered, and that answer will be given by the bit error rate and the SNR curve. Okay, So here in the for the coded systems, EB by N naught. EB is the bit energy here. EB is the bit energy, and N naught, as you know, it is the twice that of the noise power spectral density that we have considered. This is the correct metric for the coded system, and once we enter into the coded system, we will be having a normalized SNR. That means EB by N naught. We have that EB by N naught, and we establish a relationship there for the bit error rate and the SNR, normalized SNR. So signal energy per information bit is given by EB is equal to ES divided by R. ES is the symbol energy and R is the rate. Rate, if you say, rate means K divided by N, where K is less than N. Okay, that means if I am giving a K bit, I will get a N bit information from the encoder. If I am giving a K bit to the encoder, K bit message to the encoder, I will be getting a N bit from the N bit output from the encoder. So ultimately, my rate is K divided by N. Okay, in the place of 1 bit, if I am sending 2 bits, then my rate is 1 divided by 2. Okay, then the rate is very half the rate. Okay, so why we are going for this metric EB by N naught is because no more we are sending a bit energy that has been wasted for 1 bit is EB, but actually we don't do that in the encoder. We don't do that in the channel coded systems, because in channel coded system, when we are sending 1 bit, that doesn't mean we are sending 1 bit. We are sending a half a bit. It literally means that we are just sending the half a bit, and only if we transmit 2 bit in a rate half system, only if I transmit 2 bit, then only it means that I am transmitting 1 bit. Okay, so ultimately we have a total energy consumed to transmit K bits is N into ES. So that is the total energy consumed for K bits, and noise power is given by the same thing, the sigma square is equal to N naught divided by 2, and here is the SNR, normalized SNR EB by N naught, and it is represented in terms of R and SNR here, and we have EB by N naught is equal to SNR divided by 2R. Okay, so consider my BPSK system, just an uncoded BPSK system. My R will be equal to 1 because the input of the modulator will be equal to the input number of bits is equal to the output bits. So R is equal to 1 there. So we have the bit error rate as after doing all those mathematical circles, we will be having that bit error rate as Q of root of 2 into EB by N naught. Okay, there we establish a relationship between the EB by N naught and the bit error rate. Okay, so with this we will be plotting a curve. This can be either bit error rate or a symbol error rate. We can also compute the symbol error rate as well when we go for a higher order constellation. For this case, it is bit error rate. Let's say this is a comparison of the turbo coding and the uncoded system. Here we can see that bit error rate is being compared between the coded and the uncoded system. Consider the coded system is using the turbo codes, and turbo codes are anything because that's turbo codes is the most powerful codes. So that's where we will be getting a very high performance there. Okay, and here if you see the 10 power minus 6 bit error rate is achieved at 9.8 dB. 9.8 dB, around 9.8, around 10 actually. So whereas for an uncoded system, this dotted line is an uncoded system. So there we have achieved this 10 power minus 6 at some 16.2. Okay, let's say it is 16.2. So this difference is actually known as the coding gain. Okay, once we are using the coding gain, once we are using the channel coding there, we could able to achieve a bit error rate of 10 power minus 6 at 9.8 dB itself, whereas for uncoded system to achieve a bit error rate of 10 power minus 6 requires 16.2 dB. Okay, so this is the beauty of this curve, and so what is the use of this? Why we need such a performance measure there? Say we have nowadays students are very much interested with the PUBG, and it requires a internet connection. So for a high graphics PUBG game, the battery life has to be spent for that graphics and not for transmitting and receiving the information bit. So when I am transmitting and receiving at 10 power 9.8 dB and I mean SNR, I will be using the remaining energy to save the battery life so that we can play for a long time, right? So whereas if I'm using uncoded system, for internet connection itself, my 7 dB is gone, around 7 dB is gone, extra 7 dB is gone. So this is the beauty of the channel coding, and we will move on to the next slide, because this is the thing I tried to convey from the previous slides. And there are other gains too. MIMO is one thing that people talks about often, and it introduces the diversity gain. And there is one more gain called coding gain. The coding gain is what we discussed before. Actually, diversity gain will change the slope of the bit rate curve, whereas the coding gain will actually shift the bit rate curve inside. So this is clearly shown here. This is taken from Paul Raj book, and and this is the advantage of introducing a MIMO and coding to your communication system. Okay, so let's enter into the last part of this discussion, that is the low density parity check codes. And that's what first we want to know, why we are going for this coding. Then only we can go for some codes. I thought of discussing about the Hamming codes. That is one of the basic codes, but for 5G we have only this LDPC. LDPC is also a very good code. The thing is, we need to know what is a generator matrix, what is a parity check matrix, some basics on this theory of error control coding. And let's discuss something about this LDPC. We have some idea about this LDPC. There are a few terminologies. Firstly, density, because the word itself has low density. Density means when we have a binary source, we expect some number of ones, or we expect some number of zeros from that. If my density is less than that 0.5, if my density is less than 0.5, then it is known as the sparse. Okay, and this sparse matrix, this sparsity is actually contributes to the low density. Okay, that means the number of one, if I am taking a vector which has zeros and ones, it has very, very less number of ones when compared to the number of zeros. That actually means that it is low density. It is of low density, and when I keep on increasing the length, the density just vanishes, and we will be getting the sparsity there. So this actually helps in puncturing and rate matching in the 5G wireless communication. And there is another concept called overlap. The number of places this ones are getting overlap, not zeros but ones. That's why we are comparing two different vectors which has zeros and ones, and in two different places the ones are getting overlapped. So the overlap is 2 between V0 and V1. And also this is the reason for LDPC and parity check, particularly this parity check, because there are a generator matrix and parity check matrix H. These are all the very famous representation. Generator matrix is G and the parity check matrix is H. And this parity check matrix is being used for encoding in LDPC. And that's why we have the low density parity check codes. And there are two types of LDPC precisely, like regular LDPC and irregular LDPC. In regular LDPC, if we see that our column weight is fixed and the row weight is fixed. When I take a parity check matrix, column weight means the number of ones that has been in a row or a column. When I consider a row and it has only 3 ones, that means my weight is 3 there. Okay, and in this way, this regular LDPC has been constructed. I'm just running through the slide. Okay. And we have regular LDPC, and later for decoding and all those things we require this Tanner graph. This is actually given by Tanner. It is nothing but a bipartite graph that used to represent the parity check matrix, and this is particularly used for decoding, estimate the decoding complexity of the LDPC. And this bipartite graph is divided into 2 types of nodes. One is check nodes and another one is the variable nodes. Check nodes will have, let's say an example here. H is the parity check matrix we have taken, and the corresponding Tanner graph is given here. Here we can see, if I am taking the first column here, we have to see from the V0 point of view. It will connect to the second and the fourth check node. These are all check nodes. The top one is check node, okay, and the one that is given here is below is a variable node. It is denoted by V0, V1, V2, V3. Okay, so when I take the first column, it will be connected to the second check node and the fourth check node. So we will be having connections from second check node and the fourth check node. Similarly, if I am taking some random fourth column, okay, fourth column, first one and fourth one are connected. I mean, the first one and fourth one are connected here. So I'm taking V3, first one and fourth one are connected, right? In this way, this Tanner graph is being built, and these have certain properties. Let's not get into the details because these things are there to study, and a lot of video lectures are also available. Okay, so you just go through that, and there is a terminology called cycle, and another terminology called girth. So these terminologies are particularly used for decoding while decoding the low density parity check codes. Okay, and for constructing this matrix, because this is a very short, this is a very small matrix. H is just a 4x8 matrix. But when we are entering into a 5G, we will be going in the terms of thousands, 1000 cross 2000 matrix or something like that. We will be dealing with a huge number of matrices, huge matrix sizes. So we want to construct that matrix with some. We can't randomly put ones, and we have to have some logic in placing the ones in the parity check matrix. Okay, so Gallagher is one old method for constructing this parity check matrix, but still it is being used in many parts of communication systems. And what they will be doing is, so this is an example of 15x20 Gallagher's matrix. I mean the LDPC parity check matrix. Initially, we will be checking what is the allotted weight for a column and what is the allotted weight for the row. So each row should be of a weight 4. So 4 number of ones should be there in each row, and 3 number of ones should be there in every column. So first I will be placing the 4 number of ones here. Okay, because each row should have a weight of 4, and for the second row we will be placing the 4 ones in the next set. Like this will follow in this fashion. Okay, there are some theoretical explanation for this, but I'm just ignoring that. Just straight away entering into the example, and again this number of ones are placed here. In this way, we will be building up the first submatrix of 15x20. Okay, and the second and third submatrix are just a mere permutation and permutation of columns of the first submatrix. Okay, these matrices are formed from here only. Just a permutation, just a mere permutation of columns only. Okay, so in this way, Gallagher's construction is done for the parity check matrix. And there is another construction called McKay's construction. There we will be considering permutation matrix or a circular matrix. This has a weight of 1, and this has a weight of 2. Okay, and in the places of 1, we will be placing the permutation matrix. Yeah, this one means we are placing the permutation matrix in the places of ones in this picture. Okay, that means we can easily construct a matrix which has a column weight of 3 and a row weight of 6, because the weight is 3 here and the weight is 3 here. If I see from this side, we will see a weight of 6. So this is about the McKay's construction for regular LDPC, and there are also irregular LDPC construction as well. That means my row weight is different, and my column weights are different, and my row weights are same. So in this way, the regular and irregular LDPC are constructed. I'm not getting into the details of that. Okay, so and there are a lot of decoding methods as well. So when we have a complex decoder, like when we have a soft decision receiver, the complexity will be relatively higher, but we have a better rate performance there. Okay, so that's about the regular and the irregular LDPC, and I hope this is useful anyway. Yes, so with this, I'm ending here because I have skipped a lot of decoding part for LDPC, and within the allotted time, I can't explain everything. So, yes. Sir, 1 minute, sir.
Thank you, sir, for such an informative session.
Yeah, thank you, ma'am.
Participants can post their queries in the chat box. If you are having any queries, kindly post it in the chat box. Now I invite Mr. P. Kannan, sir, Assistant Professor of EZ Department, to deliver vote of thanks.
Good morning, all of you. It is a great honor to propose a vote of thanks on this special occasion. First of all, I thank Lord Almighty for giving this opportunity to conduct this webinar. At the outset, I thank the resource person, Professor Dr. M. Surender, for having presented the webinar on error correcting codes for 5G. Sir, on behalf of ECE department, I thank you for your wonderful webinar, sir.
Yeah, thank you, sir.
Next, I thank the management for their guidance and motivations to organize webinar during this lockdown to make our students and other participants enrich their knowledge in relevant fields. Next, my sincere thanks to Dr. K. Jayakumar, General Manager Development, and Dr. V. Velmurugan, Principal, and Dr. L.R. Priya, Professor Academic, for their endless support. Thank you, sir and ma'am. Further, I take this opportunity to thank Professor J. Friska, Head of the Department, for their valuable advice and direction towards making this webinar in a grand success. Thank you, ma'am. Next, I thank the coordinator of this event and all the faculty members of ECE department. Finally, my sincere gratitude to all the participants for your active participation. Thank you, one and all. Thank you.
Yeah, thank you, sir. Thank you for the opportunity, and I'm very happy to deliver this lecture here, and hope we will be meeting often in the future. Yeah, thank you.
Thank you, sir.
Thank you. So, can we cut the call, disconnect the call?
Yes, sir.
Participants,
Yeah.
participants
I'm
feed.
ready to take the questions, please. Anyone have any questions? Please go ahead.
Sir, actually, one question is there. Which is the fastest error correcting code?
Ma'am?
Sir, there is one question. Which is the fastest error correcting code?
Fastest in the sense like turbo codes, we can say that it is also a fastest one, but LDPC is the fastest one. In case of decoding, that's why it has been adapted for 5G, particularly for its decoding complexity, because the decoding complexity is very less there. It is considered to be the fastest one right now, the LDPC, along with the polar codes. That's why we combine this polar codes and the LDPC. Polar codes is just for the control information only, not for the user data. So we can say that the combination of LDPC and polar codes can contribute to the fastest of the error correcting codes.
Okay, thank you, sir. Sir, one more question. What is
Yes,
the difference between permutation matrix and circulant matrix?
Yeah, for that I will take it. 1 minute.
Okay, sir.
Yeah, here is the permutation matrix. We just take the identity matrix. Identity matrix in the sense like in the every diagonal we will be having one, and the diagonal elements will be one. There will be there will be applying the permutation for the every columns, and every columns will be permuted. Like the first column will be placed in the third one, and the third one will be placed in the second. Like that, permutations will be happening. That is the permutation matrix. Ultimately, if you see the row weight and the column weight are same, it is equal to 1. Whereas the supplement matrix, each row and we just consider this. I hope you can see my screen here. Just take the first row, 0, 1, 0, 0, 1, and the second row is nothing but the circular shift of the first row. So, and the third row is the circular shift of the second row, and consequently we can build a matrix which has a row weight as 2 and the column weight as 2. Okay, this is the supplement matrix in the Mekes construction. I hope this will be clear. Yes. Please, ma'am. Next. Yeah.
Sir, how Bowley code is better than cyclic redundancy check?
Sorry, ma'am.
How Bowley code is better than CRC?
No, actually, I am not in touch with Gole codes, because Gole codes the lengths are fixed. It actually works for some number is there for Gole codes, and cyclic redundancy check is a basic thing actually. But Gole codes are very powerful codes. I would say CRC is a basic level code, I guess. But anyway, please take a help of Google, because I haven't went through that theory of error control coding completely. But anyway, for 5G, just now the concentration is fully on LDPC and Polar.
Okay, thank you, sir.
Yeah.
Participants, feedback link will be provided in the chat box. And thank you all for joining with us. Thank you.
Thank you. Thank you, ma'am.
Thank you, sir, once again.
Yeah, thank you.
Thank you, Surendra, sir. It's a
Yeah,
wonderful webinar, sir. Thank you, sir.
Thank you, Kannan sir. Thank you.
Okay, thank you, sir.
Thank you.
Thank you so much, Surendra sir.
Yeah, thank
The
you.
webinar was excellent. The way you have presented and the way you have answered the question, really it was awesome. And really we feel privileged to have you as today's resource person.
Thank you,
So
ma'am.
thank you so much, sir.
It's a privilege, ma'am. Thank you. And also,